Hi everybody, my name is Pascal Urien. I am from Telecom Paris in France, and the title of my presentation is Proving IoT Devices Firmware Integrity with Bijective bMAC times Stampede. This demonstration presents an innovative Bijective bMAC times Stampede algorithm, bMAC-TS, running in an Arduino Nano whose code is open and published. The goal of bMAC-TS is to detect corrupted software, especially bootloader, in IoT devices. It relies on two pillars. The memory space is finite and the computing time is stable. This algorithm computes a memory fingerprint with a hash function according to a pseudo-random order fixed by a permutation P. The time required by this operation, following a normal distribution, is XOR with the fingerprint. The demonstration shows a Bijective bMAC time Stampede software probe running in an Arduino Nano 3.x powered by the ATI MEGA 328 processors. These processors comprises 32 KB flash, 2 KB static RAM, 1 KB square PROM, and a 16 MHz clock, so the whole memory space, M, is 33 KB. We chose this platform because it is cheap, a few dollars, and easy to program, thanks to the open and free IDE framework. The code source can be retrieved at GitHub. The bMAC algorithm computes a memory fingerprint with a hash function hash, such as keycac 256, according to a pseudo-random order fixed by a permutation P working in the range 0M-1. The permutation P is the bMAC key. Factorial M permutations can be defined for M memory space. The main idea is that an embedded malware cannot guess or store bMAC results due to the large entropy of P permutations. It is important to notice that unused memory, flash, SRAM, square PROM, are filled with pseudo-random values. A way to defeat the bMAC algorithm is to use a compression-decompression algorithm. A malicious bMAC entity may decompress a green code area at runtimes. Because decompression operations imply delays, the time CT needed by bMAC algorithm is measured and XOR with the memory fingerprint. So bMAC-TS is equal to bMAC XOR CT. According to the demonstrated implementation, the computing time, relying on permutation P, follows, roughly speaking, a normal distribution, illustrated by experimental results on the right figures. We notice the following parameters. Average is about 25 seconds. Standard deviation is about 12 milliseconds, which means 10 bits of entropy. We use a timer with a 4 microsecond clock, that's to say 64 processor cycle resolution. The bMAC calculation requires on average about 434 million cycles. With a precision of 64 cycles, we assume that corrupted bMAC should modify the measure's computing time. Let's have a closer look at computing time. We use permutation based on generator G key in Z modulo P, P being a prime number greater than M, the memory space. We choose a safe prime. P is equal to 2QQ plus 1, with P equal to 7 modulo 8, and Q being the Sophie German prime. In the demonstrated implementation, P is equal to 35,879 and Q is equal to 17,939. Q minus 1 generators G key are available and computed according to the relation G key is equal to P minus 2 power key modulo P with key in the range 1 Q minus 1. Permutation P is expressed as Pu is equal to F1 plus U minus 1 with U in the range 0 P minus 2. So Fx is equal to G2 power S1 multiplied by G1 power X modulo P. G1 and G2 are generators, and X and S1 are in the range 1 P minus 1. Therefore, P minus 1 Q minus 1 square, that's to say about 2 power 43 permutations, are available for bMAC calculation. Parameters G2, S1, G1 are allocated thanks to a pseudo-random number generator, which generates key 1, key 2 in the range 1 Q minus 1, and therefore G key 1 and G key 2, and S1 in the range 1 P minus 1. In the demonstrated implementation, a hash block is computed every 136 bytes. The hash block computing time is about 51 milliseconds. The average computing time between two blocks is about 0.4 milliseconds. This means that about half of the bMAC computing time is consumed by the P permutation. Because the implementation uses a square and multiply algorithm, the Px computing time is dependent on the bit of x values. The square and multiply algorithm induces a normal computing time distribution. We are going now to take a look at the bMAC code. Permutation parameters G2, S1, G1 are computed thanks to a pseudo-random number generators working with 31-bit seeds. Interruptions are disabled in order to get a stable computing time. The timer is initialized and the hash function is reset. Permutation P is computed for input value I ranging from 1 to P minus 1. A square and multiply algorithm computes modular exponentiation. The output value V is equal U minus 1 is mapped if possible to a memory cell whose content is hashed. Finally, the fingerprint is computed and the computing time is read from the timer. Here is an illustration of user's experience. Random K values K1, K2, bMAC parameters G2, S1, G1, and results, that's to say bMAC values, computing time, and bMAC timestamped are displayed every 27 seconds on a PC screen thanks to serial links. Thank you for your attention.